The power of graph algorithms, real-world applications beyond textbooks in today's interconnected digital landscape. Graph algorithms form the backbone of countless technological advancements. From social networks analyzing user relationships to logistics companies optimizing delivery routes, understanding graph theory isn't just academic, it shapes modern civilization itself. This exploration dives deep into specialized graph algorithms beyond basic introductions. We'll examine cutting-edge implementations used in industries ranging from cybersecurity to AI development, revealing patterns you won't find in standard textbooks. Mastering traversal techniques, breadth-first versus depth-first. Breadth-first search, BFS, and depth-first search, DFS, serve as fundamental tools for navigating complex webs of connections. While both can reveal reachability information, their execution methods differ significantly based on memory requirements and discovery order. BFS systematically explores nodes layer by layer, ensuring the shortest paths get prioritized. This characteristic makes it ideal for finding minimal steps in unweighted graphs, such as determining the closest hospital location given GPS coordinates. BFS uses queues, keeps track of nodes at current level before moving deeper. DFS employs stacks, explores single branch until endpoint reached memory usage. BFS requires more space due to queue storage applications. DFS excels in maze solving and cycle detection. Consider network intrusion scenarios where security teams need to trace attack paths. Here, DFS rapidly identifies potential breach vectors through recursive exploration of connection chains. Both approaches have time complexity O, V plus E, yet actual performance varies with data structure choices. For sparse graphs containing few edges relative to vertices, DFS often performs better in practice. Uncovering hidden connections, shortest path algorithms revealed modern routing systems rely heavily on advanced shortest path calculations. These algorithms transform seemingly abstract mathematical problems into solutions shaping our daily commutes and global shipping networks. Dijkstra's algorithm remains foundational in weighted graph optimization. By maintaining priority queues of tentative distances, it efficiently finds optimal routes for applications ranging from GPS navigation to telecommunication infrastructure design. Pseudocode snapshot, function Dijkstra, graph, source initialize distance array with infinity set source distance to 0 create min priority queue while queue not empty, u equals extract min node for each neighbor via view. If distance, v, distance, u, plus weight, u, v update distance, v, add to queue. Floyd-Warshall offers alternative value proposition for dense graphs, computing all pairs' shortest paths simultaneously. This approach becomes particularly powerful in optimizing airline route pricing models involving hundreds of interconnected airports. The Bellman-Ford algorithm introduces robustness against negative weights through relaxation operations. However, its linear time complexity compared to Dijkstra's logarithmic efficiency creates trade-offs requiring careful consideration. Variants like ** incorporate heuristic estimates to dramatically speed up pathfinding tasks in video game environments or autonomous vehicle navigation systems. Cutting through complexity, minimum spanning tree strategies (MST) algorithms address critical infrastructure challenges from telecommunications grid designs to climate change mitigation projects. They enable connecting all components with minimal resource consumption while maintaining full connectivity. Kruskal's algorithm utilizes union-find data structures to detect cycles during edge additions. Its greedy nature ensures optimal results regardless of starting point selection, offering flexibility in real-time implementation scenarios. Time complexity breakdown. Kruskal O, E log E, prim O, E plus V superscript 2, prim with heap O, E log V. Prim's algorithm demonstrates superior performance on dense graphs with high vertex counts. Modern implementations leverage Fibonacci heaps to achieve near-linear runtime improvements in specific application contexts. These algorithms become indispensable in power grid maintenance, enabling engineers to determine optimal locations for installing substations while minimizing wire material costs. Dynamic connectivity. Union-find data structures. Unveiled union-find structures provide elegant solutions for managing evolving group memberships. Their applications range from detecting communities in social media platforms to managing file system access permissions dynamically. The two fundamental operations, find and unite, allow tracking connected components in massive datasets with remarkable efficiency. Path compression optimizations reduce lookup times exponentially over repeated queries. Implementing union by rank. Each element maintains parent pointer and size/rank metadata. Find operation follows chain until root identified union merges smaller trees under larger roots. Real-world impact emerges in disaster response coordination systems. Emergency managers use these structures to track rescue team formations and equipment allocations in real time during crisis situations. Researchers continue refining these fundamentals to adapt to non-static environments, developing variants capable of handling streaming data and distributed processing frameworks effectively. Eulerian paths, historical insights with modern implications. Leonhard Euler's famous Königsberg Bridge problem laid foundation for graph theory itself. His solution revealed profound mathematical properties still applicable in contemporary engineering applications. An Eulerian trail exists only under strict conditions. Either all vertices possess even degrees, or exactly two have odd degrees. These rules govern everything from molecular biology studies to circuit board manufacturing processes. Algorithmic implications. Checking degree parity takes O.V. time. Path reconstruction possible via Hierholzer's algorithm. Directed graphs require balanced in/out degree checks. Biologists exploit these principles when mapping protein interaction networks, identifying pathways that traverse every known binding site exactly once. Spatial analysis software now applies these ancient mathematical concepts to optimize drone delivery routes, ensuring complete coverage of target areas without retracing flight paths unnecessarily. Sequential dependencies. Topological sorting fundamentals. Project management professionals owe significant gratitude to topological sort algorithms. These tools convert complex dependencies into executable plans, preventing disastrous schedule conflicts. Kahn's algorithm represents one efficient implementation strategy, iteratively removing nodes with no incoming edges from dependency graphs. This method works exceptionally well with parallel task execution systems. Pseudocode overview. Function topological sort. Graph compute in degree for each node. Initialize Q with 0 in degree nodes. Result equals, while Q not empty, U equals to Q. Append to result for each neighbor V. Decrement in degree of V if in degree V equals 0, and Q, V. Software version control systems utilize similar principles to manage commit histories, ensuring correct build sequences when compiling multi-module projects. Blockchain technologies also benefit from these sequential ordering mechanisms, maintaining transaction integrity through appropriately ordered ledger updates. Flow optimization. Max flow algorithms in action. Max flow algorithms represent some of the most sophisticated graph theory implementations. These tools solve allocation problems in supply chains, traffic networks, and computer hardware configurations alike. The Ford-Fulkerson method leverages residual capacities and augmenting paths to incrementally increase flow amounts until reaching optimality. Practical implementations typically combine this with Edmonds-Karp's BFS-based enhancements. Complexity considerations. Generic Ford-Fulkerson, O, F *E, Edmonds-Karp variant, O, VE superscript 2. Push relabel algorithm, O, V superscript 2 square root E. Water distribution networks apply these principles to balance pressure levels across municipal grids, maximizing throughput while respecting pipe capacity constraints. Network security analysts employ analogous strategies to model cyber threat propagation, calculating maximum vulnerability spread rates across interconnected systems. Clustering communities. Advanced network analysis methods identifying meaningful groups within vast datasets requires specialized clustering algorithms. These methods reveal hidden patterns in social interactions, gene expression profiles, and market behavior analyses. Modularity maximization focuses on partitioning graphs to maximize internal edge density within clusters versus external edges between them. This metric guides the Louvat algorithm's divisive agglomerative process effectively. Implementation phases. Initial phase assigns nodes to communities, randomly optimize local moves, improving modularity scores, construct metagraph representing supernodes, repeat hierarchical clustering recursively. Medical researchers analyze brain connectivity scans. Using these techniques, identifying abnormal neural cluster formations associated with neurological disorders. Retailers gain competitive advantage by applying these methodologies to customer purchase data, segmenting markets for targeted marketing campaigns and product recommendations. Future trends. Machine learning meets traditional algorithms. Current research directions increasingly integrate traditional graph algorithms with machine learning frameworks. Hybrid models show promise in domains requiring both pattern recognition and computational efficiency. GNNs, graph neural networks, extend message passing paradigms found in standard algorithms like PageRank. These architectures learn representations capturing structural features inherent to graph topology itself. Emerging applications. Protein folding prediction, social influence analysis, chemical compound classification, recommendation system personalization. Quantum computing presents intriguing possibilities for accelerating certain graph problems. Researchers explore quantum walks as promising alternatives to classical random walk-based algorithms currently used in web page ranking. As decentralized systems evolve, blockchain developers seek improved consensus algorithms leveraging graph properties for enhanced security and scalability characteristics. Conclusion. From fundamental traversal techniques to cutting-edge ML integrations, graph algorithms remain central to solving complex real-world challenges. Understanding their intricacies empowers programmers to tackle diverse problems across numerous domains. Continuous learning and experimentation with these algorithms are essential for any serious practitioner. Whether optimizing city transportation grids or unraveling biological networks, mastering these tools opens doors to impactful innovation opportunities waiting to be explored.